Today we are going to learn about demystifying collaborative filtering techniques. You'll understand user-based and item-based filtering, matrix factorization methods, and how to implement and evaluate a collaborative filtering model.
Collaborative filtering is a technique used by recommendation systems to predict a user's interests by collecting preferences from many users. It's one of the most popular methods in use today, forming the backbone of systems that recommend movies, books, and even friends on social media platforms. The core idea is that if two users share similar preferences, one user's preferences can be used to predict the others. In this video, we will break down the complex world of collaborative filtering into understandable segments, focusing on user-based and item-based filtering, exploring matrix factorization methods, and understanding their applications. By the end of this session, you'll have a solid grasp of how to identify, implement, and evaluate collaborative filtering models, their benefits and limitations, as well as real-world applications. User-based collaborative filtering is a method that makes predictions about a user's interests by leveraging the preferences of similar users. The process begins by identifying users who have historically rated items similarly. To determine this similarity, various measures such as cosine similarity or Pearson correlation are often employed. Once similar users are identified, their ratings are aggregated to predict the unknown ratings for the target user. This approach is commonly used in online platforms where user interaction data is abundant. One of the advantages of user-based filtering is its straightforwardness. It's intuitive and easy to implement. However, it may suffer from scalability issues as the number of users grows, and it can be less effective in sparse datasets. Despite these challenges, user-based filtering plays a crucial role in many systems we interact with daily, from e-commerce platforms recommending products to streaming services suggesting new content based on social proofs. Item-based collaborative filtering shifts the focus from users to items. Instead of finding similar users, this method identifies items that a user has rated similarly in the past with other items. The similarity between items is calculated using methods like cosine similarity or adjusted cosine similarity. Once similar items are identified for a given item, the system predicts a user's rating for a new item based on the user's past ratings and the item similarities. This approach is particularly beneficial in environments where the number of users is significantly larger than the number of items, as it tends to be more scalable than user-based filtering. Item-based filtering is frequently used in scenarios like product recommendations on e-commerce sites, where understanding the relationship between items can lead to more accurate predictions. While it offers scalability and often provides more stable recommendations, it can be limited by the quality of item metadata and may not adapt as quickly to changes in user behavior as user-based methods. Matrix factorization is a powerful technique used to reduce the dimensionality of data in collaborative filtering, improving both efficiency and accuracy. One of the most popular matrix factorization techniques is Singular Value Decomposition, SVD. In the context of collaborative filtering, matrix factorization decomposes the user-item interaction matrix into two lower-dimensional matrices, representing users and items in a latent feature space. These latent features capture the underlying factors influencing user preferences. This method enables the system to predict ratings even for items with sparse data by leveraging these latent components. Matrix factorization is particularly advantageous because it can handle large-scale data efficiently and is less susceptible to the overfitting problems that often plague user or item-based methods. However, it requires significant computational power and can be complex to implement. Despite these challenges, matrix factorization has become a cornerstone of modern collaborative filtering systems, particularly in applications like movie recommendations and music streaming services.
Collaborative filtering offers several distinct advantages that make it a preferred choice for many recommendation systems. One of the most significant benefits is its ability to provide highly personalized recommendations. By analyzing user behavior and preferences, it can deliver tailor-made suggestions that align closely with individual tastes. This method is also highly adaptable, working well across different domains without the need for detailed item metadata, unlike content-based filtering. This means that collaborative filtering can be applied to a wide range of industries, from entertainment to e-commerce. Additionally, because it relies on collective inputs from many users, it can uncover community-driven insights and trends that might not be evident through other methods. These advantages make collaborative filtering a powerful tool for enhancing user experience and engagement on digital platforms.
Despite its strengths, collaborative filtering is not without its limitations. One of the primary challenges is scalability, as the computational cost can increase significantly with the number of users and items. This is especially true for user-based filtering, which can become impractical in very large datasets. Another critical issue is data sparsity, where the user-item interaction matrix is mostly empty, making it difficult to find similar users or items. The cold start problem is yet another limitation, where new users or items have insufficient data to generate accurate recommendations. Additionally, collaborative filtering can sometimes lead to biased recommendations, reflecting the behavior and preferences of a dominant group rather than a diverse user base. This method is also heavily dependent on user activity, meaning it may struggle to provide accurate recommendations for users who interact with the system infrequently. Understanding these limitations is essential for developing more robust and fair recommendation systems.
Collaborative filtering is at the heart of many services we use daily. One of the most well-known examples is Netflix, which uses collaborative filtering to recommend movies and TV shows to its subscribers. By analyzing viewing habits and user ratings, Netflix can suggest content that aligns with individual preferences. Amazon employs a similar approach when recommending products to its users, using collaborative filtering to identify products similar users have purchased. Spotify also utilizes collaborative filtering to curate personalized playlists and suggest new music based on a user's listening history. Social media platforms like Facebook and LinkedIn use collaborative filtering to suggest new friends or professional connections by analyzing mutual contacts and shared interests. In the realm of e-commerce, personalized ads are often powered by collaborative filtering, ensuring that users are presented with products that are likely to pique their interest. These examples highlight the versatility and effectiveness of collaborative filtering across various industries and applications. Implementing a collaborative filtering model involves several steps. First, data pre-processing is essential to clean and structure the data appropriately. This includes handling missing values, normalizing ratings, and splitting the dataset for training and testing purposes. Next, selecting the right similarity measure is crucial, whether it's cosine similarity, Pearson correlation, or another metric depending on the dataset characteristics. Once the data is ready, you can choose an algorithm, such as user-based or item-based collaborative filtering, or even explore matrix factorization techniques for more complex datasets. After building the model, evaluating its performance is vital to ensure its accuracy and reliability. Common evaluation metrics include precision, recall, and the root mean square error (RMSE), which provide insights into the model's predictive capabilities. It's also beneficial to perform cross-validation to test the model's robustness across different subsets of data. Through these steps, you can develop a simple yet effective collaborative filtering model tailored to specific recommendation tasks.
Evaluating the effectiveness of a collaborative filtering model is crucial to ensure it meets the desired performance standards. Various evaluation metrics help assess different aspects of the model. Precision and recall are two fundamental metrics that measure the accuracy and completeness of the recommendations. Precision indicates the proportion of recommended items that are relevant, while recall measures the proportion of relevant items that are recommended. The root mean square error, RMSE, is another important metric, providing insights into the average discrepancy between predicted and actual ratings. Cross-validation techniques are often employed to test the model's stability and generalizability across different data subsets. These evaluation methods not only help in assessing current performance but also guide model adjustments and improvements. Continuous evaluation and tuning are essential to adapt to changing user preferences and maintain the effectiveness of the recommendation system. By employing these techniques, organizations can ensure their collaborative filtering models provide accurate and valuable recommendations to users.
Data sparsity and cold start are two significant challenges in collaborative filtering that can hinder the performance of recommendation systems. Data sparsity occurs when the user-item interaction matrix is largely empty, making it difficult to find similar users or items. This sparsity can lead to unreliable predictions and a lack of diversity in recommendations. The cold start problem arises when new users or items have insufficient data, preventing the system from making accurate predictions. Addressing these issues requires innovative strategies. For data sparsity, techniques such as matrix factorization, data augmentation, and hybrid filtering methods can be employed to fill in the gaps and enhance prediction accuracy. To tackle the cold start problem, incorporating additional data sources, such as demographic information or utilizing content-based filtering, can provide initial insights. These strategies help mitigate the impact of sparsity and cold starts, ensuring recommendation systems remain effective and user-centric. As technology continues to evolve, so do the methods and applications of collaborative filtering. One of the emerging trends is the integration of deep learning techniques with collaborative filtering to enhance recommendation accuracy and efficiency. Deep learning models can capture complex patterns and relationships in data, offering more sophisticated insights into user preferences. Hybrid recommendation systems, which combine collaborative filtering with content-based techniques, are also gaining popularity, providing a more comprehensive approach to personalization. Real-time personalization is becoming increasingly important, with systems adapting to user behavior and preferences on the fly. Additionally, there is a growing emphasis on privacy, as users become more concerned about data security. Future collaborative filtering systems are likely to incorporate advanced privacy-preserving techniques to protect user data while delivering personalized experiences. These advancements promise to enhance user experience, making recommendation systems more intuitive, responsive, and aligned with individual needs and expectations. In conclusion, collaborative filtering is a cornerstone of modern recommendation systems, offering personalized experiences across various domains. Through this video, we explored the intricacies of user-based and item-based filtering, delved into matrix factorization methods, and examined their real-world applications. We also discussed the advantages and limitations of collaborative filtering, addressing challenges like data sparsity and cold start problems. As we look to the future, the integration of advanced technologies promises to enhance these systems further. By understanding and leveraging collaborative filtering techniques, you can unlock new opportunities for innovation and user engagement in your own data-driven projects.